Hi, this is Mongo's library channel, and today I'll be talking about BSD Sockets API. What's that? That is a programming interface for creating network applications. And my goal is to share some of my experiences and understanding. And if you're like me, an embedded software engineer, then I hope it will be useful for you in your own career. Let me start. BSD stands for Berkeley Software Distribution. And to understand where it comes from, I need to go back in history. Personally, I attribute the API creation to Ken Thompson. I could be mistaken, but that's my view. Ken Thompson graduated from Berkeley in California and went working to Bell Labs in late 60s. And that, together with Dennis Ritchie, he created UNIX operating system, and they invented a C programming language. And Ken Thompson, together with other researchers, invented some key concepts. One of those concepts was a file system and API for working with files. A Unix file API is pretty simple. A user program can open a file, and Unix kernel gives a number, a numeric file descriptor to the user program, and a user program can read from that file, write to that file, and close that file. Let me show you how it works, and I'll be using a C programming language, the one created by Dennis Ritchie and Ken Thompson. A user program can open a file, and the kernel gives back an integer, a file descriptor, and using that file descriptor, we can read data from a file, we can write data to the file, and we can close the file. And if we compile and run this program, we can see that it works. In mid-70s, Ken Thompson went to Berkeley, and together with other people, they worked on the Unix operating system, and they created a version of it, which was called BSD Unix, Berkeley Software Distribution Unix. And at that time, they started to work with network with TCP/IP. Their idea was to use that file API for network connections as well. That means that Unix kernel would give a numeric descriptor for the network connection, and they called it a socket. And then a user program can read from that network connection, read from a socket, and it can write to the socket. But since network connections were a bit different from usual files, a bunch of other calls were added to create connections, but the input-output, read and write, was pretty much the same. Let me show how that works on an example of a simple web server. So now I'll create a very primitive, very simple web server using BSD Sockets API. So a socket call creates a new descriptor for the network connection. Then bind and listen calls, they make that descriptor a listening connection. And then we fall into infinite event loop. And in the loop, we accept new incoming connections from that listening connection. And every new incoming connection gets a new descriptor, new socket. And right now, I'm just printing that we accepted the connection and closing the socket straight away. So, and we see that it works. The next step is to add the code that read an HTTP request from that connection and writes a response. So let me do that. An HTTP request ends with an empty line. So we need to read from a socket until we get an empty line. So yeah, this is how it works. We've got a new socket by accepting that socket from a listening connection, and then we can read from that socket, and note we are reading in a loop until we get the full request. And when we are done, we write a response. And notice that the interface is identical to files. We use read syscall and we use write syscall. And when we are done, we just close the socket, close the connection. So it looks pretty simple, but there is a catch with that. And the catch is that these calls, read and write, can block. Unlike files, network connections are not predictable. So when you read from a file, you are sure to get data or you fail straight away. But when you read from a socket, you don't know, like the data might just not come. That is easy to demonstrate on a simple test program. So we have our server running here and we have our client, and let's make one client to block. So instead of using curl to send request, we use netcat. So I run netcat localhost port 9000. And instead of writing the whole request, I write just a part of it. So if I hit enter, that's going to be the full request. So I hit enter and I got a response. But if I don't hit enter, it's a partial request. So our program is stuck in this loop, reading request. And when it is stuck in this loop, the listening connection cannot accept any other socket. So let me show you that. We create a new request, and here if we do curl, it is stuck. And that is a problem. And what to do with this problem? One way to solve this problem is to use fork. A Unix operating system has a way to start new processes. It's called fork and exec. So a fork system call creates a clone of an existing process. And we can use fork to continue running this read loop in a totally separate process. Remember, back in the times, there were no threads. All programs were single threaded. So let me show you how it's done. Here how it works. A fork system call, it's called by one process, but it exits in two processes. It exits to the caller process, and also it exits to the cloned process, to a new child process. And the return value from the fork, it's different. So it returns a positive number, the PID of the new process, to the parent, and it returns 0 to the child, right? And that's how we can differentiate, are we in the parent or in the child? So if we are in the parent, we do not read at all from the accepted socket. I can close it straight away and go to the accept again. And if we're in the child, we read everything, we read the request, we write the response, and then we simply exit the whole process. So that's how it works. And in this way, it does not block anything. So you see, I can start a new request, even if it's partially written. A new client can make requests with no problems. Okay. So this trick works, but if we are continuing our file analogy or file paradigm, you wouldn't fork a process every time you want to work with files. And also there could be a lot of processes. So forking thousands of processes to work with network connections, it might not be an optimal thing. And by the way, an early web service and early network programs, they used exactly this mechanism. But what if we want to handle all connections in a single process? So what we can do, Let me remove that fork trick. So what we can do to avoid this blocking thing, one thing we can do is to make those system calls read and write and accept non-blocking. And that's exactly what was done. We can set a special flag on a file descriptor, which is called a non-blocking flag. And that non-blocking flag makes all operations on the file not blocking. Assume that we do that, and the accept call will be non-blocking and read call will be non-blocking, and our program then needs to be able to handle many connections simultaneously. And that means that the current structure of our program is not really suitable, because the current structure, it handles only one connection. So we need to rearrange the structure of the program to handle many of them. We'll create a structure for every connection, and that structure will keep a file descriptor, a socket, and a buffer, and the current number of bytes read from the socket. And then in that infinite loop, we'll read from all the connections, right? So we'll first accept from the listening connection, and then read from all the connections. And if they have data, we'll do basically the same logic. Okay, so let me do that. This is how a structured program works. We have a connection structure. I've added a new flag is closing, a helper function add connection to add a new connection to the linked list. And you can see that for every added connection, I call this function fcntl. This function sets that magical non-blocking flag. That non-blocking flag makes all operations on the given file descriptor non-blocking. And the restructured program looks like this. We create a server with an empty list of connections, then we add a listening connection to the list, and then we fall into infinite loop. And on every iteration of that loop, and by the way, let me a bit restructure this piece. So I refactor every iteration of that loop into a separate function called server poll. So yeah, this is how it works now. So on every iteration of the server poll, what we do, we traverse all active connections, and then for every connection, if a connection is listening, we look, okay, does anyone try to connect to us? And if not, we just go to the next iteration. And if yes, we add the accepted connection to the list of connections. Okay. And now if a connection is not listening, if it's an accepted connection, we try to read from that connection. And then if we fail and there is a special error number, it's called E again. And it means that if a descriptor is marked as non-blocking, then there is no data yet in that file descriptor, that we fail with this error. Okay, so, and if it fails with that error, we just do nothing. And then if we read 0 or -1, so if it fails for some other reason, we just set the closing flag. And then if we read some data from the connection, we just add that data to the buffer, and then check, did we receive the full request? And if we did, we just respond as usual. And after we did respond, we set the closing flag. Okay, then after that, we have a second loop, and we again iterate over all connection. And for those connection that have closing flag, we just close them. All right, so this is it. That's how it works. And as you can see, we can start a server and we can start a new connection, which is halfway through. Okay, so and then it does not block other connections. So I can create new requests, and as you can see, they execute happily, and I can execute the original connection. So everything looks cool. Great. Um, Now we have a server that works in a single process and handles many connections. But again, there is a catch with this. And the catch is that since all the connections are marked non-blocking, and if there is no data on all connections, then this loop, this outer server loop, becomes a busy loop. So essentially, we are executing on 100% CPU. And let me show you that. So if I start a terminal and run top, so we can see that our program BSD runs at pretty much all CPU, okay? And that's bad. So we solved pretty much almost everything. We have now a server that handles many connections, but it eats the whole CPU time. So how we solve this? And the solution for that was to create another call and add this call to the BSD sockets API, and that call will solve this CPU issue. The idea is that we can bundle all the sockets together, all the connections together, and have a special system call saying, hey, Unix kernel, this is a list of the sockets that I'm interested in. So please go and go check them, and please block and don't use CPU time on that. And then when any of those sockets is ready to be read, return. Okay? And it was made so. And the new system call was called select. And it solves this CPU time issue. So let me show you how that works. I've added a new flag, is readable, to the connection structure. And here is another concept of BSD sockets API, file descriptor set. So we create a set of file descriptors, we nullify it, and then we iterate over all our connections and add every file descriptor, every socket to the set. And then when we are done, we call this select call, saying to the kernel, please go and wait until any of the sockets is ready to be read. And then when select is done, when it exits, and we can give a timeout to the select, but I didn't do it. So last argument is the pointer to the time value, but I gave it null, meaning that select should wait indefinitely until any of the sockets is readable. And then we iterate again and set this is readable flag. And here in the next loop, when we iterate over all our connections to read them or accept them, we just check that flag, and if the connection is not readable, we just skip it. So that means that this system call select saves us. So it lets kernel uh, waiting in that system call until any of the sockets is ready and not lose any CPU time. In the later versions of BSD API, there were other calls added to that, like poll. Other Unixes added alternatives like Linux added epoll and so on, but the idea of all these multiplexing calls is the same. Let kernel wait until any of the file descriptors is ready. So, and as you can see, we can now run the server, run multiple clients, and I can run multiple requests and get responses. So, and if I check the CPU usage, it's all good because we are not, so our program is not even on the list. Now we have a working, primitive web server that works in a single process and handles multiple connections. All good. But if we take a look at this, our program became really complex. So if you compare it to the original small, simple program, it's nothing like that. It's really complex. If you look at that, it's really difficult to figure out what it does, and it's by no means similar to the simple sequential kind of read file, write to file paradigm. So the nature of the network, the unpredictable nature of network connections make this quite difficult. So how we can make it easier to use? And one way to make it easier to use is to turn the API of this network application to be event-based. In other words, make it more like JavaScript-like. We have a concept of a connection here, and what we can do, we can add a so-called event handler function for a connection. And then for every interesting event which happens in the lifetime of a connection, for example, creation event, closing event, reading data event, or a new web request event, we can call a handler function. So let me show how that works. I added a so-called event handler function to every connection, and I've added a list of events. And then in my program, I implanted event triggers. So when I create a new connection, I trigger event open. When I close a connection, I trigger event close. When I read the data, I trigger event read. And when I receive a full HTTP request, I trigger event HTTP request. And now what it gives me an ability to move the logic of the connection to the event handler function. So now we have connection event handler, which is pretty easy to understand. So we see which events are created for the connection, and we can add reactions to those events, pretty much like in JavaScript. So when we have an HTTP request, we can craft a proper HTTP response. And now the whole structure of the program also looks simple. We create our server, our listening connection. For the listening connection, we specify event handler function, and then we fall into infinite event loop. So now if we start this server, we can get the same functionality we had before. And if you take a look at the Mongoose library, which is a lightweight TCP IP stack that our team develops, it's here on GitHub, tezanta/mongoose. Then the structure of the application is very much similar to what I came up with here. So you can see the same event manager, we initialize it, we create a listening connection, we give it an event handler function, we fall into infinite loop, and here is an event handler function handling an HTTP request. So that was it. That was my understanding of BSD sockets API, why it was created like that, why we have those weird select poll function calls. And also, I've demonstrated how to transition from the BSD sockets API to the event-based API. So hope it was useful for you. Take care. See you in the next one.